Please join me in welcoming to the Distinctive Voices podium, Dr. Irene Lee.
All right, thank you everyone. I want to thank you for two things. First, thank you for coming here, and hopefully, there's an audience out there in the virtual world. The second is I want to thank you for bringing the rain away from Seattle and bringing it down here. It's been actually quite a beautiful day up in Seattle, I heard. I'm going to structure this talk in sort of three sections. The first is a general introduction to some of these concepts of AI, ophthalmology. And then the second is sort of my journey through this space and how we got to sort of where we are today. And then finally, I want to end by talking about a really exciting project that will hopefully change the way that science is done in the future. So, I hope everyone in this audience realizes that we are firmly living in a different era as human society. We are living in what people are calling the fourth industrial revolution, where very powerful machine algorithms are doing, processing the oceans of data that is invisible around us today. So every time you pick up your phone and you type something into, your search engine or you compose an email, there are very powerful algorithms that are reading and watching and processing how you interact with all your electronic devices. I always like to start these talks by kind of disambiguating these terms a little bit because I feel like the news media uses these terms interchangeably, but they actually have formal definitions. So the field of artificial intelligence as a whole is very old. It's been around since the dawn of modern computing. And there's a subfield within artificial intelligence known as machine learning. And within that, there's a subfield known as deep learning. And all the advances we hear about on the news today, like ChatGPT doing XYZ, is really in the field of deep learning, which means all deep learning is artificial intelligence, but not necessarily vice versa. And to understand what deep learning is, you sort of have to understand what artificial neural networks were. And artificial neural networks actually were very, very popular in the 60s and 70s. And there was a time back then that there was talk of artificial intelligence sort of taking over the world and replacing jobs. And that was known as sort of the AI summer of the 80s and 90s. And that obviously sort of fell away. And now we're sort of in a new AI summer. But the big difference was that those models from back then only had about 1 to 3 layers. There was really a limitation in what they were able to do computationally. And so in my opinion, there were sort of 4 advances that didn't happen at the same time, but they kind of collated together to create this moment that gave rise to what we call deep learning today. First, it was this realization that computer graphics cards, so the kids who have gaming computers that have these very fancy graphics cards in them, it turned out that the math that you use to rotate polygons in 3-dimensional space could be used to solve linear algebra problems. And if you recasted the way you look at machine learning, it turned out to be a series of linear algebra problems. And so all of a sudden, these graphics cards that were being developed for computer gaming could be used for computation in deep learning. The second was the use of these things called convolutional filters that could take advantage of the local coherence in images. So, if you have one pixel, the pixel next to it are often very similar to that first pixel. And these filters were able to exploit that coherence. The third was something known as a nonlinear activation function. And finally, probably most importantly, our computer hardware and architecture had evolved to a point where it was possible to collate and collect huge amounts of data that you could use to train these models. And that's why we live in this very exciting time today, that as you feed these models more and more data, and you make the models more and more complex, even with hundreds, if not thousands of layers, the models seem to exceed human performance. So I want to shift a little bit and explain why in the field of medicine, ophthalmology was sort of perfectly poised to take on AI. So first, there's a huge sort of clinical need. So if you ask the US population, what are you most afraid of losing? It turns out eyesight is ranked number one. And then if you ask them among the different medical conditions, being blind was ranked as high as Alzheimer's disease and cancer. So people really care about not going blind. And to enable this technology in the clinical space, there was a imaging modality known as optical coherence tomography. And you may have not heard of it. It's often abbreviated as OCT, but it's actually very commonly done. So if you walked into an optometry clinic at a Costco, it is extraordinarily likely that your eye would be imaged by one of these machines. In fact, it's very hard to walk into any eye clinic in the world and not have your eye imaged by one of these machines. And the reason is that it's non-invasive, and it's very quick. It only takes a minute. And it provides a level of detail that was impossible to see before. And it has rapidly become the most commonly obtained ophthalmic imaging modality, if not medical imaging modality in the world. So what is this OCT? What does it look like? So this is a picture of one device, and what it provides is almost like a CT scan of the retina in cross-section. And it provides an ability to sort of see through the layers of the retina and see what's going on underneath the retina in a way that was impossible before. What is sort of tragic is that outside of the field of ophthalmology, if you asked, what do imaging of the eye look like? Most people think of images like this, a color image of the retina where you can see the optic nerve and the vessels coming out. But we actually very rarely collect that type of imaging in the clinic because it doesn't show us anything more than we can see when we look inside of somebody's eye. But this OCT, it turned out, could show us much more, and it became a pivotal a portion in the clinical decision making. And to sort of prove to you that it provides microscopic detail, on the right side here is a histology slide of the human retina. And you can see the individual cells here. And those nuclear bands, or those dark purple bands, translate directly to the dark bands that you can see on the OCT slice. And so, this led to a point in time when vast imaging, volumes of imaging data have been collected through routine clinical care in ophthalmology. And it turned out that the eye shares many features that with the rest of the human body. So the vessels, the tiny vessels in the retina are identical to the vessels that you find in the kidney as well as in the ear. And the retina itself developmentally comes from the human brain. So it's actually part of the central nervous system. And so if you want to understand what's going on in somebody's brain, it's very hard to take a biopsy of somebody's brain, but it's much easier to look inside of somebody's eye. And then finally, there's this a problem where the aging population is rapidly outstripping our supply of doctors. And so it turned out that the field of ophthalmology really needed AI tools. And so when this convergence of technology came, it became sort of a flashpoint. And I don't know if you all know who Eric Topol is, but Eric Topol is a famous medical technologist, and he tweeted that of all the medical specialties, most people think radiology is leading AI, but it's actually ophthalmology. And I firmly believe that even today, this continues to be true. So I'll take you through our journey of AI and deep learning in ophthalmology. When I joined the faculty at University of Washington, one of the first things I did was I extracted all the imaging that was available in our clinical data set. And that amounted to 5.5 million of these OCT images. And then because I had access to the electronic health record and it was stored in a structured database, I could extract the clinical elements of the clinicians who have been seeing these patients over these decades of time and match the imaging to the clinical labels. And at the time, it ended up being sort of serendipity what happened because I collected this data set, and I had nothing I could do with it. It was just sitting on my hard drives because there was no real methods I could take advantage of. And one of my friends suggested, who was in the technology field, he suggested, you should try this thing called deep learning. And I said, oh, that's just a fad. It's not going to work. And he said, no, you should try it. And he convinced NVIDIA to send me a graphics card. And so we took that graphics card and we designed sort of our first deep learning experiment. And this was it. We tried to see whether a deep learning model could take images of the OCT of people's retinas and distinguish between somebody who was totally normal and somebody who had macular degeneration. And if you're not familiar with age-related macular degeneration, it causes central vision loss, where people are not able to make out the faces of their grandchildren. And so from our data set, we assembled about 100,000 images, and we trained this model called VGG16. And in a day, we got this result. And so this is known as a receiver-operator characteristic curve. And this measures the performance of a diagnostic model, and perfect is 100%. In this problem space, clinicians get around 95%. In one day, we had taken this data set that we were not able to do anything with, and we had trained a state-of-the-art model that could be used to distinguish and find people with this blinding disease. I was very nervous when I got this result because it looked too good to be true. And often in science, if it's too good to be true, it usually is. And I had no way of double-checking, that this model was doing anything useful. And it gets to this problem that we hear about today, this black box problem, where we don't really understand why the models are doing what they're doing. And so I dug around the computer vision literature, and I found this post-hoc visualization method that was very intuitive. And the way it works is very simple. If I give you this picture and I ask you, is there a ball in this picture? You would say with 100% certainty, there's a ball in this picture. If I cover up a small part of this picture and I ask you again, you'd still say yes. And if I continue to iterate over every possible position of this box in this picture, eventually the box will end up here. And I'll ask you, is there a ball in this picture? You'll say, I'm not sure anymore. And so that's what we did. We took images that the model had never seen before, and we systematically occluded different parts of the image, and we watched to see what happened to the model making the decision that this was macular degeneration. And when we did that, so for reference at the top here, you have a normal OCT retina of the fovea. And these are 3 clinical examples. If you generated a heat map using this technique with this model that we had trained in a day, we got this result, where the model was clearly highlighting areas that matched the clinical pathology of macular degeneration. And that gave me much more certainty that deep learning was not a fad, that it was actually very, very powerful. And that's what sort of led to our confidence in moving forward with this line of research. The second paper that we published way back when is sort of a different problem, and it has to do with the outlining of these dark areas on the OCT that have to do with fluid. And this, just to put it in perspective, it takes, about an hour of somebody's time to laboriously trace each one of these dark areas on a full volume of OCT scans. And what you're seeing on the right here is the deep learning model that was trained to do this task, and it's able to do this as well as human beings. And when I first got this result, I was very excited, and I showed some of the people who had been working in this field for a while. And they said, oh, Aaron, that's great, but it's actually not that impressive. All you have to do is find this top layer here, and that's not that hard to do, and you have to find this bright band, and everything that's dark in between is just fluid. And what I pointed out to them is that, actually that's not true. If you use that idea, that doesn't work when you have something like a blood vessel. So this is a blood vessel here that's casting a shadow. And this is an artifact. It's not actually fluid there. And if you use that sort of heuristic, it would be incorrect. And so what was really nice to see is that the deep learning model was not making that mistake. And so, like I said, we sort of did this experiment to show that it did as well as human beings did. But the reason why I always show this example is because of this video. So what we did here is we really slowed down the rate at which the deep learning model was learning. And so up here, you see that OCT scan where there's that shadow. And when I play this movie, you'll see that the model initially highlights the area as red. And then over time, as it's fed more and more examples, the model learns that, oh, that area is actually not fluid. And this area underneath the retina here is actually not fluid inside of the retina. And it continues to get better and better and better. So, but the really hair-raising thing about this video is something that happened at the very beginning. So I'm going to play it again, and I'll pause it. So right here, when it's sort of going through that exponential learning phase, it on its own had decided that there was another problem it had to first understand. And it decided that it needed to know what the layers of the retina are, that this is the top part of the retina and this is the bottom of the retina, and that everything in between was more likely to be fluid, just like I sort of explained to you a minute ago. The deep learning model had to learn to identify a subproblem that was not in the direct pathway of what we were asking it to do. And yet it identified that problem and solved it. And I view that as sort of an example of emergent AI behavior. So, from these very early experiments, we learned that, machine learning is sort of always limited by ground truth, but it seems to have this incredible potential. And so our lab started to think of ways to push AI and deep learning to do a lot more. So I just have a few really quick examples of what we've managed to accomplish over the years. One is the quantification of these images of the retina. And here what we're looking at is the retina sort of mounted on a slide. And it used to be that graduate students who were trying to get their PhDs would spend hours outlining this yellow area and all these little red areas here that represented areas where blood vessels were growing abnormally. And it would take them 7 hours to do one image. And their whole PhD would be doing this for a batch of experiments. So we trained a deep learning model that could do this, and then we deployed it on the web, and we allowed people to just upload decades of experiments that could be quantified in minutes. And it totally transformed this particular field and accelerated the pace of research using that technique. Going back to macular degeneration, our group worked with Christine Curcio and Cynthia Owsley at UAB, and we designed a framework that could pull out new features in the retina that clinicians had never been aware of being important for macular degeneration, using a completely data-driven approach using machine learning. So it's possible to pull out things that have been buried in the imaging all along that we had not been aware of being very, very important for disease using these techniques. And this is kind of a really fun example. We trained a deep learning model that could identify the landmarks around the eye, so like the eyebrow, the eyelid, as well as the sclera and the iris. And you can see us coloring them. And we did this because there's a branch of ophthalmology that has to do with lid surgery, where the position of the lids are very, very important. But what happened is that Julia Owen, who this is a picture of, who's the lead scientist on this, she was bored at home during COVID. And so she convinced her husband to take her iPhone and turn on the slow-mo feature and take a video of her blinking. And so this is, I'm playing this movie slowed down substantially because what's being plotted on the x-axis here is in seconds. And what we are able to do using this very simple setup of an iPhone with the slow-mo feature, we're actually able to quantify and measure the dynamics of the upper lid during normal human blink at sub-millisecond resolution in a way that was impossible before. To explain what the state of the art looked like before we did this work, this is what somebody used to have to wear. there would be a magnetic coil that would be taped to the upper lid and a whole apparatus that would measure the excursion of the lid over time. And we are able to kind of do all of this and more just with an iPhone and a deep learning model. One thing I'll say that we're particularly sort of excited about this line of research because we believe that the upper lid dynamics might give us insight into what's going on in the brain. For example, in Parkinson's disease, we suspect that the upper lid dynamics may be affected, and we will be able to measure that using this technique. Our group has done some work outside of the field of ophthalmology. So we've worked in the space of radiology, where we've transformed traditional regular MRI images of the brain into MRA images that usually have to inject a dye into the human body for. And we've even been able to use traditional imaging to transform and understand how the different regions of the brain are connected. And this whole line of research sort of gets at this idea that in the treasure trove of all the imaging that has been captured by all the hospitals around the world for all this time, there's still secrets that could be pulled out using these techniques. I want to kind of explain, spend a good amount of time explaining where we're going next. If you take a step back and you think about what are the necessary ingredients to make all of this magical AI happen, it really boils down to sort of three things. One, you need really smart people. You need AI scientists. You need these special accelerated computing platforms that can do these linear algebra operations. And most importantly, you need the data. If you look at all the things that are happening with ChatGPT and that's happened with self-driving cars, it's happened in an area where data is abundantly available. And unfortunately, in the medical space, in the biomedical sciences space, getting access to data is actually very, very difficult. And if you think about what data sets are sort of ideal for doing deep learning, you really need them sort of to be large. And when I say large, I don't mean having relatively few people and knowing a ton about them, but I mean having a lot of people with relatively few pertinent measurements on them. You want diverse pathology. You want them to be balanced for sex, race, and ethnicity so that they don't have bias. And ideally, you want them to have images or waveforms inside of them. One of the great data sets that are available for biomedical research, it comes out of a project from the United Kingdom called the UK Biobank. And the UK Biobank is an extraordinarily impressive effort. In approximately 500,000 people, they have done everything from imaging their eye, their brains, doing whole genome sequencing on them, and collecting a whole host of data on them without a single hypothesis. It's a biobank that was meant for discovery. Over the years, it's generated about 15 petabytes of data with about 2,000 ongoing global research projects. 1,400 papers have been published and 200 have been in the Nature family journals. So it's been tremendously successful. And if you look at some of the things related to this topic of pulling out new things from ocular imaging, the folks from Google have published this paper where they showed that using just a color image of the retina, they could predict the age, gender, whether they were smoking, what their hemoglobin A1C was, what their body mass index was, and what their blood pressures were. They've also shown that you can predict the amount of calcium that's been blocked up in the coronary arteries, as well as the level of anemia from using deep learning. So it's been a really, really impressive result that they've been able to do. But there's sort of an Achilles heel with the UK Biobank, and that's this problem of bias. So if you needed to do all these things on 500,000 people, you have to do what's called convenient sampling, meaning that you set up a recruitment center and you invite anybody who's willing to walk through the door to be part of your study. And that led to what's known as sort of the healthy volunteer bias. People who were healthy were willing to undergo all this medical testing. And it ended up being that even common diseases are fairly uncommon in the UK Biobank. The other big problem is that it's very heavily white British. In fact, it's 94.5% white British. This bias of healthy volunteer, if you quantify it, looks like this. So if you measured the mortality rate by age group of the UK population, it's this dark line here. If you take the people in the UK Biobank and you measure their mortality rate, it's actually about 10 to 15 years later. And so they're extraordinarily healthy white British people. And everything that we've learned from the UK Biobank is on extraordinarily healthy white British people. The other sort of criticism I have of the UK Biobank is that it is, because of the sensitivities around the data that has been collected, there is a tremendous amount of paperwork and red tape you have to overcome to get access to this data set. In fact, when we tried to get access to the data set, I believe it took us 3 or 4 years before they were willing to send us the data. So it doesn't really fulfill what has become known as the FAIR criteria, which is findable, accessible, interoperable, and reusable. I would argue it's not exactly the most accessible data set in the world. And so the NIH in the United States saw the tremendous success of the UK Biobank, and they created sort of 2 programs. One program is known as the All of Us program, and it's structured in a very similar way to the UK Biobank. The other program was known as Bridge to AI. And the way that they did this is that it wasn't one part of the NIH. They realized that this really needed to be from the entire Common Fund program, meaning that it spanned across the institutes of NIH. And their big goal is to generate flagship data sets for AI in medicine. My wife and I, so my wife is also a clinician scientist, and we are a husband-wife partner in science, and we marshaled our vision for what this project should look like in about 2 months and wrote an 800-page application. And by some miracle, we ended up being one of the 4 data generation projects that was awarded to build a flagship AI data set. So our project is known as the AI-Ready Equitable Atlas for Diabetes Insights. So it's centered around type 2 diabetes. And the goal is to create a multidimensional, ethically sourced data set in diverse people for studying salutogenesis in type 2 diabetes. And hopefully you understood most of those words, but you probably did not understand this word, salutogenesis. So what is salutogenesis? Hopefully most of you have heard of this term, pathogenesis. And pathogenesis is the process in which the human body or tissues go from a healthy state to a disease state. And pathogenesis has really been the focus of, most of biomedical research. We spend a tremendous amount of time trying to understand the biochemical pathways that we can intervene on with different therapeutics and drugs to halt or slow this progression from healthy to diseased. Salutogenesis is actually the reverse of pathogenesis. How do you actually take the human body and revert it back to a completely healthy state? And there's been a very little focus in building data sets or studying this process. So we put together a very big team where Cecilia and I are leading these 6 different modules. The first module is the team science module. So the NIH realized that when you have a big, diverse group of people who've never worked together before, you need team science. And so there's a group from Stanford that are team science experts that are leading the team science module. We have a skills and workforce module that's being led just down the street here at UCSD. And they're building modules to make this data set useful for the next generation of AI researchers. We have an ethics module that's being co-led by folks at Johns Hopkins University as well as UCSD. We have a tools module that's being led by OHSU, and a data module that's being led by UCSD, UAB, and University of Washington. And finally, I'm co-leading the standards group with somebody at Johns Hopkins. So what is this idea? How can you possibly study something like salutogenesis if it's never really been studied before? And so what we proposed to do was to borrow this idea that came out of single-cell RNA-seq. So if you're not familiar with this technique, what you do is you take a population of cells and you separate them into little buckets, and you do transcriptomics on each one. So you measure the level of the different forms of RNA in each cell separately. But if you do that and you keep track of where all the transcripts are coming from, you can apply a machine learning technique called manifold learning, where the job of the manifolds are to put two cells that are very similar in their transcript profiles right next to each other, and two cells that are very different, very far apart. And as long as it obeys sort of that metric of cells being similar being close and cells that are dissimilar being far apart, they can fall along these manifolds where you can see the transition of cells going from very embryonic stage to terminally differentiated stage. And so even though we're not measuring across time because this is collected at a single time point, we call this axis pseudotime because we're witnessing the transition in this population of cells. So our proposal is to scale this up to the level of a human being. And what we're trying to do is collect enough data from the different parts of the human body that we know are important for diabetes, and assemble them, hopefully later, along these manifolds, where one axis is pseudotime, and the other axis is going from disease to healthy. So we'll be able to study both salutogenesis and pathogenesis. So what is exactly in our data set? One of the things that we realized in medical research, and it's not a criticism, but it's an unfortunate reality, that when you assemble a data set, people get very excited about studying one disease, and that 99% of their data set is of that disease. And unfortunately, they have very little that are healthy. Or you have something like the UK Biobank, where it's extraordinarily healthy and you have very little disease. And so what we propose to do in our project is to uniformly sample along the disease axis. And so we identified 4 strata of diabetes that were important. So one is obviously not having any diabetes. The second is lifestyle controlled. The third is oral medication controlled. And finally, the fourth is insulin dependent. And what we're trying to do, which is extremely difficult to do, and I believe has not been done at this scale, is to build a triple balanced data set where 1,000 of the participants will be white, 1,000 black, 1,000 Asian, and 1,000 Hispanic. And within that, 1,000 will be normal, 1,000 lifestyle controlled, 1,000 oral medication controlled, and 1,000 insulin dependent. And within that, one-to-one balancing between males and females. And the overall idea of this is that if somebody takes this data set and trains an AI model to take X and predict Y, then it will be balanced for race and ethnicity and sex. And so the models should not exhibit any kind of bias. So what are we collecting in our data set? We're obviously collecting a medical history, asking what kind of medications and surgeries somebody's had. We're collecting demographics and vitals, a whole host of blood and urine markers. We're doing surveys, including social determinants, health, and depression. We'll do a battery of cognitive function testing. We'll collect a 12-lead EKG. We'll do some visual function measurements, and we'll do a whole bunch of ophthalmic imaging modalities to capture the state of the retina. We'll send participants home with an Apple Watch and a continuous glucose monitoring device for 10 days. And then we've built a custom environmental sensor that can measure the particulate matter inside of somebody's home to understand what kind of air they're breathing at night. We plan to do some form of genetics as well as bank all the samples for future research. And most importantly, we hope to open source this data set. And what I mean by that is that anybody with an internet connection anywhere in the world will be able to click and download our data set and start using it for doing AI research, and they won't have to sign a mountain of paperwork before they can access this data set. Some of the project goals and challenges we hope to solve along the way, obviously getting a whole bunch of people who've never worked together to work together well. We hope to build teaming insights, promote diverse perspectives, really think about the ethical considerations of building such a data set and making it free for everybody. Fostering community engagement, understanding how to format the data in a way that could be used and reused in the future. We are planning to build a cloud-based infrastructure for sharing and accessing this data, and we really hope that this data set will be used to train the next generation of AI researchers and bring more expertise into the biomedical domain. And so, our project is basically everything sort of in this green box here. And what we're planning on doing is releasing this data set as we collect it. And so rather than this old model of people collecting a data set and squeezing every last paper they can possibly think of out of it before they release it, we're releasing the data set as we generate it. So as early as next year, we will be releasing this data set. And what we hope to do is that people will then, not us, but other people, will be able to enable them to build models that can try to understand how things related to the EKG might be related to diabetes severity, or that things in the retina might be related to cognitive function. Or look at genetic data and try to predict time to needing insulin. So, where are we going with all of this? I hope you all believe now that novel insights into disease will be unlocked with AI. They have been, and they will continue to be. I believe that we can use AI to elevate the standard of care around the world. I think collaborative data science is the future. So hopefully people are realizing that now, if we come together as a community of scientists and clinicians, we can build data sets to answer questions that have been impossible before. And, I was wrong. I think AI is actually here to stay. So I just want to end by thanking, all the members of my lab and my funding sources, and I'd be very happy to take any questions.